Hello viewer and welcome to the e-learning classroom. So today we want to look at the practical on current against the voltage, whereby now we are going to plot a graph and then we'll be able to determine the EMF together with the internal resistance of the cells. So we have the setup here. We have the ammeter, we have the voltmeter, the cells, the nichrome wire, and then we also have a table which we are going to fill and then to solve the questions. So the first thing, we arrange the apparatus as they appear. So we have the cell holders. Maybe we can put the cells. Can put the cells on the cell holder. So let's see what we have there. So we have the cells in the cell holder there. So they are here. The cells in a cell holder. We have the voltmeter somewhere here. This is the voltmeter here. The voltmeter here. Then we also have after the voltmeter, we have the ammeter somewhere aside here. We have the ammeter somewhere aside here. And then we also have a switch assigned here, the switch close to the cells. And then we have the nichrome wire. So I have my nichrome wire here. Maybe the scale is 0 to 100. So that is how the apparatus are arranged. Maybe I can put this one aside here. So from there now, what we do the connection now. We can do the connection. So let's start with the positive terminal here. So we have one wire coming from the positive terminal. One wire coming from the positive terminal of the cells. This is a wire coming from the positive terminal. So at this point, we have a junction whereby we have now two more wires. A junction of two more wires. Let's make that junction of two more wires. So I have my two wires here. I want to make a junction there. So maybe these two wires I can clip them here to make that junction. So these are the two wires. These are the two wires from this junction. One wire goes straight to the voltmeter because we are starting from the positive terminal. So we connect to the positive of the voltmeter. For our case, we can connect at 5 volts. And then the other wire goes straight to the ammeter, which I'll also connect to the positive because we are starting from the positive terminal. So from there now, we have this junction here. So one wire comes from the ammeter straight to the nichrome. So one wire comes from the ammeter. For the ammeter, I can use the scale of 0 to 1. So one wire comes from the ammeter. We are using 0 to 1 straight to the nichrome. So for the nichrome, I can input it at 0. For the nichrome wire at 0, let's see. So back up to 0 there. Up to 0 there. Then from there, we are done with the positive side. We go to the negative side. One wire from the negative terminal. One wire starting from the negative terminal of the battery. That is the negative terminal. And then this wire, at this point, we have a junction of two wires. So we first make that junction of two wires. Let's make that junction. Can use these two wires to make the junction. The junction there. So for these two wires, I can clip them here to make that junction. So these are the two wires now. And then one of these two wires goes straight to the switch, from here to the switch, so straight to the switch there, and the other wire goes straight to the voltmeter. The other wire goes straight to the voltmeter, and because we're in the negative terminal, we'll connect to the negative side, and then we are now in the switch. One wire also comes from the switch straight to the nichrome, and for that maybe I can use the last wire from the switch straight to the nichrome. So from the switch here, the last wire comes straight to the nichrome wire. For the nichrome, maybe you can input it at 20. At 20. So after we are done with the circuit now, already you can see there's some reading reflected on both. Already you can see there's some reading. So let's first maybe disconnect here to safeguard ourselves, so that we familiarize ourselves with the scale, and then from there we can take the readings. So we have the voltmeter. We are using the scale of 0 to 5. That is the lower scale, and for that scale you realize that 10 divisions are representing 1. So one division is 0.1 volt. Then for the ammeter, we are using a scale of 0 to 1. That is the upper scale, and that means 10 divisions is 0.2. So one division is 0.02 ampere. These are the accuracies. So with that now, we can now go to the readings. So let's first close the switch. Let's first close the switch, and then we take the readings now. So can close the switch there. So we are at 20 centimeters. So we have the voltmeter, the potential difference. The reading for the potential difference is 1.7. We can record the readings. 1.7. Then for the ammeter, we are using the upper scale. For the ammeter is 0.44. These are 24 divisions. So 24 times 0.02, that is 0.48. Current is 0.48. So we go to 30. We just push this one up to 30, straight to 30 there. Then we take the new readings for the current and voltage. So for the voltage, we have 1.8 volt, 1.8. Then for the current, these are 19. So we can say 19 times 0.02, which gives us 0.38. 0.38. We go to 40. We just push this one slowly, gently up to 40 there. Straight to 40. So at that point now, voltmeter reading is 1.9. 1.9. Then the ammeter reading, we have, these are 16. So 16 times 0.02, that is 0.32, 0.32. Then we go to 50. We just push this one straight to 50, there. So for the voltmeter, we have 2.0 volt, 2.0 volt. Then for the ammeter, these are around 14. So 14 times 0.02, that is 0.28, 0.28. Then we go straight to the next one is 60. We push it up to 60 there. That is 60. So for the voltmeter reading, it is still at 2.0. This one is still at 2.0. Then for the ammeter, these are 12. So we have 12 times 0.02. Remember, we are working with the accuracy here, which is 0.24. 0.24. Then we go to 70. We go to 70 there. So we push this one up to 70. So voltmeter reading is 2.1. 2.1, and then the ammeter reading is these are 10, so that is 0.20, 0.20. Then lastly, let's push it to 80, lastly, all the way to 80. So we have it at 80 there. So for the voltmeter, it is still at 2.1. Still at 2.1. Almost heading to 2.2. This one is 2.1, almost tending to 2.2. So let's say that is a 2.2. Then for the ammeter, we have 9 divisions. 9 times 0.02, which is 0.18. 0.18. So these are the values we have now. These are the values we have for this practical. So we'll be using these values to plot the graph. So viewers, we can now use these values to plot our graph. So the first thing, we draw the axis. So we first draw the axis. We start with the y-axis. For this case now, because we are plotting voltage against current, it is the voltage axis. So we start with the first axis here with an arrow. So the first axis here with an arrow. Then we draw the second axis here, down here. Again with an arrow. So we have the second one down here with an arrow. That is the voltage, the current axis. So we have drawn this other one here. Maybe you can label. This one is voltage, or let's say potential difference. Potential difference. V in volts. Potential difference V in volts. And then on this other side we have current I in amperes. Current I in amperes. So, and with that now what we do, we look at the scale we have. For the current, the smallest is 0.18 and the largest is 0.48, let's say 0.5. So if you are going up to 0.5, let's say 2 squares are 0.1, 0.2, 0.3, 0.4, 0.5. So we can go with 2 squares to represent 0.1. So that means here 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. That is for the current axis. We can now look at the y-axis, or maybe the potential difference axis. So if you look at the values we have here, you realize that the smallest value is 1.7, while the largest value is 2.2. So that means maybe we can work with 2 squares to represent 0.5. So that means here we'll have 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, maybe lastly 4.0. So that is our scale. That is our scale now for the values we have. So once we have the scale now, it's good we know the accuracy of our scale. It's good we know the accuracy of our scale. So if we start with the current axis, you realize that we have 10 divisions, 0.1. So, and that means, because you have 10 divisions, 0.1, each one division represents 0.01 ampere. And then for the potential difference axis, we have 10 divisions representing 0.5. That means one division represents 0.05 volts. So that is the accuracy of our scales. So, and what we do now from there is that, let's see the first one. These are 1, 2, 3, 4, 5, 6, 7 values. So maybe 1, 2, 3, 4, 5, 6, and 7. So let's start with the 1.7 divided by 0.05. These are 34 squares. 1.8 divided by 0.05. These are 36 squares. 1.9 divided by 0.05. These are 38 squares. 2.0 divided by 0.05. These are 40 squares. Another 2.0 is 40. Then we have 2.1 divided by 0.05. These are 42 squares. Lastly, 2.2 divided by 0.05. These are 44 squares. And then we can go to the current values for the current axis. So we start with 0.48 divided by 0.01. These are 48 squares. So these ones are direct. 48, 38, 32, 28, 24, 20, and then 18. So those are the values we have. So let's go straight now to the plotting. So we have, for the current, 48 squares, then we rise up 34 squares. So 48, 10, 20, 30, 40, 48 here. Then we write 34. 10, 20, 30, 34. So 48, 34 is there. And then we have 38, 36. 10, 20, 30, 38. We write 36. 10, 20, 30, 35, 36. 36 is there. That is 10, 20, 30, 36. Then we go 32, 38, 10, 20, 30, 10, 20, 30. So 32 is here. We rise 38, 10, 20, 30, 35. We have 38 there, 38 here. That is 38. And then we go to the next one. That is 28. So we have 10, 20, 28. We rise up 40, 28. So we have 10, 20, 30, 40. 40 is there. Then we go 24 again, 40, 10, 20, 24. We rise up 40, still there. And then we go 20, 42. So 20 here, 42 is here. 20, 42 is there. Then last three, 18, 18, 44. So 18. Then we rise up to 44 up there. Those are the values. Those are the values we have. Those are the values we have for the graph. So from those values now we obtain the line of best fit. The line of best fit for these values. So that means we look for the line of best fit here. The line of best fit here. Let's see what you can get there from our values. So the line of best fit seems to be somewhere here. So we draw that line. So this is our line of best fit now. This is our line of best fit for this graph. You can see how this line looks like. So, and with that line now, we are told determine the slope of your graph. Determine the slope of your graph. So for the slope, we look for the two readable points. Two readable points. So maybe we can pick 2 points which are easily readable. So let's say I can pick this point here and another readable point here. So these are my 2 readable points. The 2 readable points should not be very close to each other. Should not be very, very close to each other. So I have my 2 readable points here. Let's see what they appear like here. the two readable points. So we have these points values here. So this one is 0.5 0.53 0.53 1.5 0.53 1.5. For this other side here we have 0.8 0.80 against this is let's see, these ones are 10, 20, 30, 40, 45, 48. 48 times 0.05, that is 2.4 because we have 48 times 0.05. These are the values we have. So with that, now we can go straight to the slope of the graph we have. Remember, in mathematics, you normally say slope is given by change in y against change in x. But for this case now, our slope becomes, for this particular case, so slope is given by change in voltage divided by change in current. That is a change in PD all over change in current. So in that case, the values we have, if the left hand is above the right hand, according to this graph, if the left hand is above the right hand, then the slope must be negative. So that means the slope here will be 1.5 minus 2.4 divided by 0.53 minus 0.80, and this one gives us negative. So let's see, this one gives us negative what? 1.5 minus 2.4. This is negative 0.9 divided by, into bracket, 0.53 minus 0.08. This gives us negative 2. And because we are dividing voltage by current, it means that value is in terms of ohm, because it is a voltage over current. Then you are told, given that EMF equals V plus IR, find the values of EMF and the value of internal resistance. So let's start with EMF. So if you rearrange this equation, so we'll have, let's say we take negative IR this side, this IR this side, we will have V is equal to negative IR plus EMF. That is when we take IR this side, so we have this. And then from here you realize that this V is this one. That means this is like in the form of Y is equals to mx plus C. Because Y is V axis, which we have here. Current is here, which is X axis. And that means slope represents negative R. In other words, we can say down here, negative R is equals the slope. And then EMF is the intercept, because C is y-intercept. Y is equals mx plus C, whereby if y and x are the y-axis and the x-axis, m is slope and C is the y-intercept. So that means E, which is our EMF here, is a V intercept. So we can say EMF is equal to V intercept. In other words, the point where it cuts voltage axis, and that means we'll have, these are 10, 20, 30, 40, 50, 51. So 51 times 0.05, that is 2.55. That means EMF is equals to 2.55 volts. 2.55 volts. We have read it from there. And then the internal resistance we have seen is the slope. Because you can see here when you remove X, which is I, what remains is negative R. Because this is negative R times I. That means negative I is slope. So negative R is equals to negative 2. And that means the internal resistance is equal to 2 ohm. The internal resistance becomes 2 ohm. So that is how we solve that practical. And those are now the values of that practical. You realize there is a correlation between this practical and the previous one, where we also got the internal resistance to be 2 ohm. So that marks the end of today's session. Let's see you in the next session.